So we want to continue our discussion of balancing redox reactions in acidic solution. And let's see what happens when we have reactions that contain oxygen, hydrogen, water, acid solutions, and see how that plays out, carrying this balancing of redox reactions a step further. We're going to do the same thing up to the very last step. We're going to do the same thing we've been doing. We're going to show that this strong acid is going to ionize. We're going to rewrite this as net ionic. So we've got H plus NO3 minus. HI is also going to split. It's a strong acid. I'm not going to write the H plus again. I've already written it once, so we'll just combine those together. I minus for the iodide. Remember, if it splits, it gets a charge. If it splits, it gets a charge. So don't leave those charges out or they're wrong. So NO plus I2 and H2O, none of those are going to ionize. They're all either, well, they're all molecular, so they're not going to ionize. So there's our net ionic reaction. So let's look at our oxidation numbers or charges. Hydrogen's already +1. We know oxygen's a -2, which if we have a total -6 charge here, and nitrate, remember, it has to be set equal to its charge of -1. So that means nitrogen's got to be a +5. We've seen that before. My +5 didn't come out very good, but that's what it's supposed to be. Iodine is already showing as a -1. Oxygen -2, so nitrogen +2. 0 for my iodine, and +1 for hydrogen, -2 for oxygen, as it always is in water. So our substances oxidized and reduced, it looks like iodine is going to be oxidized from negative up to 0. And nitrogen is going to be reduced from +5 down to +2. So those are our substances oxidized and reduced. So let's write those as our half reactions. We've got I minus reacting to form I2. And we've got NO3 minus. I'm going, you know what, I'm going to write that a little bit further over here. You'll see why in a few minutes. NO3 minus is reacting to form NO. Remember, we've got to balance these by mass and then by charge. So 2 iodides here, which is going to result in a 2 electron change, since we've got that negative to 0 change happening twice. So that's a 2 electron change. Once again, we have to balance by mass and charge. We know that nitrate is going from the nitrogen is going from a +5 here, over here with the nitrate ion. I'm going to do that in green. I don't want to see that in the final reaction, but +5 for the nitrogen, +2 for the nitrogen on the right-hand side. That's a 3 electron change. So we know we're changing 3 electrons. So we've got a 2 electron change on top, 3 electron change here. Now, here's the step further that we've got to worry about, and that's the oxygens. Yes, we've balanced the electron, the charge change that's happening with those electrons, but we have not balanced the oxygens. Since this is an acidic solution, there are 2 things that we have an unlimited supply of, and that's H pluses and H2Os. We can use those wherever we want to get whatever we need balanced. And the rule is to always get the oxygens balanced first. If you notice over here on the left, we have 3 oxygens and only 1 oxygen over here. So it looks like we are missing 2 oxygens on the right-hand side. And the way we make up for oxygens is with water. So we're going to add some water over here. Think about how many we need. We've only got 2 right now. We need another water. We need 2 waters to balance out those oxygens. So now we have our 3 oxygens on the right, 3 oxygens on the left. But what did we mess up when we did that? We messed up hydrogens. We don't have any hydrogens on the left, but remember, we've got all the H pluses we want to work with. So looks like since we added in 4 hydrogens on the right, we're going to need 4 H pluses on the left to get that to work out. So now what do we need? We need to get those charges balanced. So I'm going to multiply that top one by 3, the reduction one by 2. And how is that going to play out? That 3 is going to change this into a 6 in front of the iodide, 3 in front of the I2, and our 6 electrons. That takes care of this. And the 2 is going to change my hydrogens to 8 hydrogens, 2 nitrates, 6 electrons, 2 NOs, and 4 waters. And that's going to take care of that too. So now electrons cancel. I'm going to be left with 6 I minuses, 8 H pluses, 2 NO3 minuses. On the other side, I've got 3 I2s, 2 NOs, and 4 waters. The last thing we want to do is to make sure our charge is balanced. And if you look at what we've got -6 here for the iodides, -2 for the nitrates, and +8 for the hydrogens. That is going to balance out perfectly our 0 on the other side for our charges, making sure that they're balanced. So it looks like this is a good reaction, and we can box it, and that is this reaction balanced. Okay, so let's look at our final example here. Going to do the same thing we did with the other one. This one's going to be a little more complex. We're going to ionize the strong acid, HNO3. So it looks like everything else is going to remain unchanged because they're either molecular, it looks like everything's either molecular or element. So we're going to have sulfur plus H plus NO3 minus. Remember, if it splits, it gets a charge. SO2, NO, and water simply carry down because they're molecular. So now let's find our oxidation numbers. We know that sulfur is 0. It's an element. We've already established that hydrogen is positive. And we just did nitrate above, and nitrate is nitrate is nitrate. It's not going to change. It was a -2 and a +5. Oxygen is a -2. There are 2 of them, so that's a -4 for the oxygen, which means sulfur is going to be a +4 to balance that out. We've seen this before too. Also, -2 for oxygen, +2 for nitrogen. And of course, our water is always +1 for hydrogen, -2 for oxygen. So oxidized and reduced, it looks like sulfur is being oxidized from 0 up to +4. And nitrogen is being reduced from +5 down to +2. We just saw that happen. So our half reactions, I'm going to write this a little further over here just so we stay out of our own way. We've got sulfur reacting to form SO2. And we've got NO3 minus reacting to form NO. Remember, this is a 0 for sulfur, +4 for sulfur on the right, +5 for nitrogen, plus, whoops, I wrote that wrong, didn't I? Let's get rid of that 3 and make it a 2. Or actually, we don't want anything at all. NO. I'll get it right here in a minute. Okay, so let's try that one more time. +2 for nitrogen. So it looks like for our electron changes, we've got sulfur already balanced, but we're going to need 4 electrons on this side to get our oxygens to, our charges to balance. And now remember, Once we get that done, we still have to worry about our oxygens. This is an acidic solution, so we've got all the water and hydrogen ions we need. Looks like we need 2 water molecules on this side to balance out. I'm sorry, I put them on the wrong side, didn't I? 2 water molecules on this side to balance it out. So I've got 2 oxygens on the left and 2 oxygens on the right. And now that I've got those 4 hydrogens on the left, I'm also going to need to have my 4 H pluses over here so that I'll have my hydrogens balanced. And at the bottom, we just saw this one in action. So we know we need 3 electrons for this one. We know that we need 2 more waters on this side to balance our oxygen. So we'll have 3 waters on the right, or excuse me, 3 oxygens on the right and 3 on the left. And since I now have 4 hydrogens over there, I'm going to need 4 hydrogens on this side. And what's our next step? Balance our electrons. Looks like we're going to need to multiply this side by 3, this particular reaction, and this particular reaction by 4, so that we'll get a 12 electrons in both cases. So let's multiply through here. Sometimes our numbers start getting a little big. It looks like this is going to be a 6 here, a 3 in front of the sulfur, 3 in front of SO2, 12 electrons, and 12 hydrogens. And on the bottom, it looks like we're going to have 16 hydrogens, 4 nitrates, 12 electrons, 4 NOs, and 8 waters. So now we have electrons canceling. We've used our multipliers there. We've already multiplied through, so now let's write our total reaction. We've got 6 waters and 3 sulfurs, 16 hydrogen ions, and 4 nitrates on this side. Be very systematic, guys. You can miss things so fast on these, and if you mess up one charge, these problems just explode. So 3 SO2s, 12 hydrogens. That didn't turn out right. I wrote that 12 pretty funky. 12 hydrogens, 4 NOs, and 8, I'm going to squeeze it in here, 8 waters. So now that we have our total reaction, what we want to look for are things that appear on both sides of the reaction. Now, this is a balanced chemical equation, so we can't just get rid of completely anything that appears on both sides of the equation that are the same. We have to think about how many we can cancel out. And let's look at waters for our example. We've got 6 water molecules here. We've got 8 squeezed in over here on the end. We can get rid of all of these, but think about it. We still have 2 left over here. So we still have 2 water molecules on the right, none left on the other side. Now, what else can we do that with? The hydrogen ions. We've got 16 hydrogen ions here, 12 over here. We can get rid of all 12 hydrogen ions here, but how many are left on the other side? 4. We can't just mark them out. It's not like spectator ions. So when we rewrite this equation with those changes, we end up with 3 sulfurs, 4 hydrogen ions, and 4 nitrate ions. And on the other side, 3 SO2s, 4 NOs, and 2 H2Os. And let's look at our charges. We have 0 charge on the right, no oxidation numbers on the right showing, and 4 positives and 4 negatives on the left. Those cancel out to 0 as well. Both charge and mass are balanced. That is our final balanced redox reaction.